we're gonna have the last session of the day with folks from Bela, who came all the way from the UK and from Germany just for us. So, is it Aiden or Adan?
It's actually Adan.
Adan, sorry. Okay.
It's all right. I mean, I live in the UK, so no one really gets it.
Yeah.
Right.
How do they say in the UK? Like Aiden or?
Aiden or Anam. Like, no one actually.
Okay. Okay, so Adan. Okay, so Adan and Clemens from Bela, and yeah, this is going to be the last workshop of the day. So enjoy.
Hi everyone. I'm sorry to disappoint. We're not going to play with FPGAs now.
Wait.
Oh, microphone. I mean, I'm Spanish, so I'm naturally loud. But yeah, I guess the recording is not like that.
Okay, I can take care of it. Just
Okay.
Okay.
Sorry for the rest of the Spanish in the room for that statement. So yeah, I don't know. Like for those that it's a little bit of an interactive workshop. We start by introducing a little bit the C++ API. But the idea is that you actually get to play with it if you brought a laptop in. If not, I would suggest that you team up with someone that brought a laptop. You need 2 USB ports because we are going to use a driver, and that needs extra power. But if you don't have an extra USB port, I also brought a power USB hub. So you're welcome to grab one. Like Clemens can give. We actually have 9, I think, because I brought one. Yeah. So yeah, I mean, shall I start introducing the workshop? So, I mean, you've been to the talk this morning, so most of the stuff that's here is probably. Yeah, if you want one, go and grab it. So this is what we do. This is Bela. That's the. Yeah, this is the small sister of the big Bela that you're going to be playing with today. That's kind of the original one based on the Beagle Bone Black. We did this small one, which is the Bela Mini, based on the Pocket Beagle, and we hope to have new Belas to show hopefully soon. But in the meantime, I'll show you a little bit how we design our workflow for C++. You can also use Faust for Bela. You can use pure data. You could use Super Collider. You can we kind of pride ourselves on saying that Bela is polyglot, and that this is actually thanks to the people from Faust that also kind of work with us on the integration. Some people that also are Super Collider coders and work with us, etc., etc. But today we're going to do C++ just because the workflow is quite straightforward. It's the kind of default API on Bela. If you work, for example, pure data, it will work with libpd, and then you will have some C++ running as well, and there's a C++ wrapper. So, oops, sorry. So C++ is the default, right? Okay. So the board that you have in front of you, or if you don't have it in front of you, is this one. It comes with a few of the things that I mentioned this morning. You have analog inputs and analog outputs, digital I/O, stereo audio in and out, all of them jitter-free and aligned, the sample line. And it also comes with a nifty, I think it's 1-watt amplifier speaker, and peripherals like I2C, etc., etc. I2C is broken out there for convenience on an all MOLES KK254 connector. I mean, these details. But yeah, today we're going to actually use the stereo input at the end of the workshop. We're going to use the stereo speakers, but we're not going to use any of the digital IOs nor the analog inputs and outputs. Instead, we are going to use the sensor that is connected, that is on your board and on mine, which is also part of our design and things that we created to bring capacitive sensing basically to the maker community. And it's an I2C sensor that has. Sorry, I'm just going to go to the sensor first, and then I'll come back. Yeah, that's the sensor. So this is what we call a Trill Bar. So it allows you to track movement based on capacitive sensing on one dimension. You can have up to 5 touches. You can measure the contact surface that you're touching, and you can use that to create interactions. In this case, we are going to use that as a driver for interaction, for generating haptics and also some fun sounds that Clemens programmed for us today. Okay. So if you have your board, you should have two USB cables. You should connect both to your computer. One is going to be the standard USB cable that is going to have all the communication, that is going to serve the IDE on your browser, etc., etc. The other one is just for powering the drivers. Normally, you just need one, unless you want to use the drivers. You need a little bit extra juice that you. I mean, you can jumper around things and try to see if you can get enough power from one single USB, but I don't want to. Yeah, let's try not to reboot anyone's computer. Or at least anyone's USB drivers. Okay, so once you're in, you can go in a browser. Firefox, Chrome, they work. Edge, if someone has that installed. And once you're in the browser, you can basically access Bela for programming. So you plug Bela onto your computer, launch the browser, wait a little bit for the IDE to be served, and you can access it on these different addresses. If you're on macOS or Linux, Bela.local should work by default. If you're on Windows 10, the IP is 192.168.6.2. Everything else 190.168.7.2. And if anyone has any problem with that, now is the time to raise your hand, and I will give you a hand with that. And you also, yeah, and as I said, you need the USB to barrel cable just to power the drivers. I'll leave that one on for a little bit, and then you can connect the boards and go on. Okay.
Will it work the same if we were to plug an Ethernet cable directly in our local network?
It should work. Yeah, it should work on with Ethernet on the local network. It will. The thing. It wouldn't serve the ID. Yeah. Actually, I think it should. Yeah, I think you should be able to access the ID on Ethernet. I haven't tried. Like last time I used Ethernet on this board was before that, before the ID was even a thing. But yeah, definitely. Like the Ethernet peripheral is available, and you can use that over network. Yeah. Some people have used it, not myself actually. But yeah. Is anyone able to access the IDE? All working? Good? Okay. Okay, I'll move. If anyone else has any trouble, Clemens is going to be around for the first bit, and then I'll be around for the second bit. Okay, so if you open the IDE, you see that you can. There's a code editor in there with some code probably showing, and then a few things down the side. We have a range of examples that one can try in different languages, most of them in C++. You have a tab where you can actually look at the files on your project and add new files or edit the project or download it or delete it if you got bored of it. There's another tab on which you can set the settings on the board. That's the hardware settings, ranging from the block size, the number of analog channels that you want to use if you were using analog channels, the sample rate of the analog channels, which changes depending on how many channels you're using, headphone level, like the PGA, which is the programmable amplifier gain at the input, etc., etc. Those are settings that you can change. You also have settings for your specific project, which are compile flags, for example, that you might want set like for having like a more verbose output or like a faster performance or a specific set of things. There's documentation for all of this. I'm not going to get into details. Hopefully the settings, each project saves the settings, so they are not shared within projects. Each project has its own set of settings, and in this case, all of them should work by default. You should not have to change anything. But if you were using headphones, maybe you should try to tune the headphone output to your liking. Okay, then there's also the pin diagram, which is quite useful, which tells you which pins on because we break out a few of the pins from the Big Bomb Black, and then we also break out the ones that we use on Bela. So it's good to know which are which. I don't know if you can see it there, but you will surely be able to see it on the browser. You can know what function it is, where is the digital pin that I want to use, the analog outputs, analog inputs, even power and ground. So that's for whenever you're plugging things on the board and prototyping. As I said, in this case, unless we, there's little to no error, unless we plugged in the I2C wrong, and you'll know in a bit, and then it's easy to fix. Okay, so the API. I don't know. I said earlier that Bela works on Xenomai, and there's a callback that is called on Xenomai, but we also have the PRU aligning all the inputs and outputs and serving those to you. Of course, that's written, but there's an API that is exposed to the user that's much easier to use. So there's three main functions on the Bela API. One is the setup, where you do all your allocation, memory allocation, whatever you need to do. The other one is the cleanup, which is when you're done with your beautiful audio code, you get rid of all the garbage that you might have generated in the meantime. And the important one is the render, which is the one that is called by the audio callback synchronously. So this is an example of how to write a simple sign generator on the Bela render. We have the context variable, which gives us the important information about the state of the board, in a sense, the context, like it gives us the number of audio inputs and outputs that are available. It gives us the sample rate, etc., the number of audio frames, and it also gives us access to the API. So this is passed, and you can also pass user data. If you were to wrap up this function somehow, you could pass the user data. Or if you were to do another call to this function, you can pass extra data into that. But basically, everything that runs in here runs once per block. You have specified the block size on your Bela, and this runs one per block, right? Here we're iterating over the audio sample, so whatever is inside that for loop runs one per sample. So if you want to write a sample by sample code, you know that the latency, as I said earlier, is going to be twice the size of your block divided by the sample frequency. But everything that happens here happens in one sample cycles. If you do something here that takes, on average, longer than one sample to compute, you're going to screw up your deadlines. So you should perhaps think about doing it differently, which is what we're going to show later. So you see that we are generating the phase of a sound wave. We are wrapping up the phase, and then we are writing it to the output. And this runs one per channel. So you write the audios and inputs are interleaved. You can write to them in an interleaved manner. You can write to them in a de-interleaved manner. It's a bit up to you, but there's this nice API function that allows you to write to this channel this output, which is probably what most people want to see, I hope. So you write on a specific frame, specific channel, and you write the value. This is already what I said. So setup runs once at the beginning, then you start the audio callback that is called repeatedly. And it's the one that gives you access to the buffer where all the inputs and outputs are ready for you, and the cleanup code. Okay, so today's theme is of the workshop is about haptics and feedback, and I think it's something that you can achieve quite a lot of nice things with very little code, and then I thought, okay, let's do a run of that, and then I'll let you guys experiment. And the way we are achieving haptic feedback in this case is with a transducer, or with a driver that is at the bottom of your board that you will be able to see, and the 1 watt amp that's included on the Bela board. These have an audible range, so we can actually use them also to create auditory feedback, and that's the second part of the workshop today. But if you use them at low frequencies, you can generate nice feedback effects. Okay, this is a particular thing. So, okay, the project that you should have open now should be called PAW-22 driver test. And if you run it using this button, now we are going to get a lot of vibrating boards, hopefully, if everything is working. Yeah, that's one. So if you run it, you can go to the GUI. Actually, I'll do that. I'll do this myself. It's gonna be a fun one. Okay. Okay. So I'm gonna walk you through a few of the features that are available here. So that should be driving the actuator already for you at a specific frequency. I'm going to drive mine. I got the boards without screws, so mine is going to actually jump out of the board. That's mine. If you come here to this small tab, you can launch the GUI and change a few of the parameters there. So this is a GUI that is basically communicating to Bela through a WebSocket, so you're able to feed back back and forth information through the WebSocket. And in this case, we have these small sliders that we're using for control parameters. So this is called once per block, and it gathers the data from the GUI and it maps it to something. In this case, the frequency of the oscillator, the frequency of a modulator, and then, I mean, this is intended, so you could hook up headphones and listen to it. So there's a haptic amplitude for the haptic oscillator and amplitude for the audio oscillator. So yeah, I have mine. Mine will be like standard mobile phone ringing. It's time to wake up. Yeah. Okay. So I mean, this is just to make sure that your drivers are working. If they are not working, then we need to figure something else for the rest of the workshop. Okay. I don't know where I put my presentation. Oh, there you go. Okay, so those are the controls, as I said. About how the code is structured. We have that render call that is generating a few oscillators. It's wrapped up in a library so that you don't need to see all the phase wrapping and that sort of stuff. But basically, the code that you can see on your render is that of generating the oscillators. But we are controlling the amplitude of those oscillators by means of the GUI. In this case, we have a few sliders that we have set up with our controller. This is our setup. This is where we say, okay, we want to add two sliders to this controller, and then on render we are getting the value from those sliders once per block. It's as simple as that. There's a little bit of kind of WebSocket connection and handling on the library, but for prototyping this is good enough. Okay, so we go back to Trill Bar. Now we're gonna explore a little bit like a few kind of like haptic effects on the bar that we have there with the oscillator. So as I said, this allows us to track movement in one direction, up to 5 touches. In most cases, we're just going to use 1 touch for this purpose. But we're going to use simple audio modulation techniques to create haptic sensations. That's the Trill Bar on your board. And here's where things get interesting. The Trill Bar is an I2C device. And today I talk a lot about the importance of sampling sensors together with audio at audio rate, and having the render callback that is kind of like a real-time guaranteed. But I2C is not real-time guaranteed, right? But we still want to be able to communicate with that. How do we do that? Xenomite has a primary mode on which it runs our audio code that has higher priority than anything else in our system. But we also can run Linux process at lower priority. So what we're going to do now is going to create an auxiliary task, which is going to run a lower priority than our audio thread that is going to gather the data from the I2C, wrap it up nicely, and then we should be able to use it on a render call. Of course, if you are not careful with the kind of with how you handle this data, you're going to notice jitter as part of the interaction, right? Because this runs whenever your audio callback is finished. So it's not gonna be sample aligned. So in this case, we create an auxiliary task, which is an infinite loop that runs whenever the audio callback gives some space, and it's gonna gather the data from the I2C and package it up for us. So this is what goes on setup, and this is a little bit what happens in the loop. So there's a loop that says, while Bela is still running, do some stuff, and then sleep for a little bit for a predefined time. But this is what's happening in the thread that runs at the lower priority, in the kernel thread. Okay. So yeah, in setup, of course, we are not going to show the whole I2C handling in this case. We wrote a nice library for the touch sensors on which you can set the address, the type of sensors, and then just use it to read the locations on the sensors, read the number of touches on the sensors, and then for whenever you make a touch, store the location of the touch and the size of the touch in an array. And then that array is going to be accessible by both threads so that you write you write to the array on this thread, and then read from the array on the audio thread. As simple as that. The first example that we have is a little bit of a visual example, just to give you an idea of how the Trill sensor works. So if you want to go onto, I'll do it here. If you want to go into projects, there should be one called Trill Visual. And if you run that one, it's going to take a while to compile. That's the thing, we are compiling. The nice thing about the toolchain is that it's self-contained. So it serves the files through the IDE. You can edit the files. You can do all the things that we're going to do through the IDE, but then it also compiles on the board. So it takes a little bit longer to compile that way we're getting into your laptop. You can do distributed compiling if you want. There's ways to set that up. But for today, I thought this would be enough. So if we come here and then come to this, to the GUI, where we had the sliders before, we'll have a representation of our Trill Bar. And then if you have several touches on the Trill Bar, you can see the location, the size of the touch changing, and then up to 5 touches. These don't come in they don't come in a specific order, but you can have you can see how reactive it is. I mean, this should work every 5 nanoseconds, so on. But as I said, it doesn't matter what's the latency of your I2C transaction, since it happens at a lower priority thread. Jitter might be a thing that you need to take into account. Hopefully not for these applications, but you can tell me at the end of the workshop. Okay. So everyone got to try that? Works for you? Okay, so your trills are working, that's good. That means that we write the I2C the proper way around. If you wanna interact with it and see how it sounds, you can run the Trill, PAW-01 Trill sound, which uses the size and the touch to modulate a few oscillators. This is one of these examples on which having a really simple generator but rich interaction could go a long way. You can, can I zoom in? The resolution is fixed so that it can be streamed. Oh, like that? Yeah, there you go. So now we have an orchestra of sine waves that you can control with your fingers. And now I'll let you decide how reactive that is. It's leave it up to you. For me, it's quite fun, even though it's just a few oscillators. But yeah. Okay. Yeah. In the well, actually, this should be the second one. Well, anyhow. Okay. So if you're ready after making a few weird sounds, we can try haptics now. So there's the first example that I have on haptics is basically it will trigger the driver for a few milliseconds at low frequency whenever there's a new touch on the board, and then the vibration frequency is going to be a scale on the number of touches. So if you have one touch, it's going to be a lower frequency. The more touches that you have, the higher the frequency is going to be. And this is a little bit to explore how you can create different sensations at different frequencies. So as you see, I have the number of active touches that I gather from my non-audio thread, and I'm mapping the frequency from 0 to the number of touches to a range of frequencies that I set up in there. And then I have an oscillator, which is like I think in this case it's a simple, it may be a sawtooth oscillator. I need to check that, but it says the frequency based on that. Okay. So if you try that one, PAW-02 Trill A, you should no longer hear the board. I mean, you can hear it rattling, but you should no longer hear the oscillators. But now you should feel that every time you touch the board, there's, oh, mine is still with them. There's a haptic sensation program for you, if it builds. Yeah, there you go. So if you add one touch, it will react to it as a haptic button would do. If you add more than one touch, like the frequency will change. Oh yeah, yeah, and screws might pop out of the board. Sorry, that's because I travel with this on the plane. Okay. Okay, but this is, I mean, like having a Linux microcomputer to trigger a few haptics is fun, but it doesn't get a long way. Let's try to make it a little bit more interesting. With the second one, I'm going to try to build to a small simulation that I did with really simple tools of surface roughness. So the first thing that we're going to do is we're going to map the touch size to the amplitude of the oscillator that generates the feedback. If you touch it slightly, then it should generate a small vibration. If you touch it with your whole finger, it will generate a bigger one. So if you go to PAW-22 Trill B, that should be the second one. Okay. So you can see now it's like now the driver is going to stay on when you touch it, but then if you touch it with a little bit of your finger, it's gonna vibrate with certain amplitude. If you put your whole finger on top of it, it's gonna go a little bit more intense. Okay, and then if you move your finger across the surface, you will see that the amount of touch that you put on top of the Trill Bar, together with this simple interaction, already creates a different sensation, right? Like a different sensation on how the surface behaves. Let's try to do something a little bit more interesting then. What if we just modulate the amplitude of this oscillator? We have a second oscillator that, based on the amount of touch, generates modulation, an AM modulation on top. So this is actually this is what I just did. Sorry, this one. Sorry, Trill Bar C builds a little bit on top of that. The idea is that now we are gonna map the touch location to the frequency of the oscillator instead of the amplitude. The amplitude is still gonna be mapped to the amount of touch that you put. But in this case, instead of taking just the position or the amount, we are going to look at the velocity. We're going to look at how, and this is quite interesting. We can dig into the code lately. How do you compute the velocity of something that doesn't happen at all your thread, right? You need to get the last readings that you had before, subtract from the previous readings. But what's your clock? How do you update that? It's easy to do, but it's a little bit interesting how you need to change your mindset just to do that. But in this case, basically, we are taking the velocity of the movement across the slider, and we are mapping that to the amplitude of the haptic oscillator. Which means that if you touch it slightly, it should be quite smooth. If you dig into it a little bit more, it should generate like a harder sensation of roughness. I don't know if that. I mean, this is me. This is not scientific at all. This was me trying to figure out a few nice interactions. So if you don't think it simulates roughness at all, then tell me. Okay, still building mine. Sorry. So the idea with this is, I mean, we introduced how to use Trill in a non-priority thread. We showcased how to do really simple haptic interactions with audio modulation objects and really kind of like simple concepts, and try to do something interesting with it. What we're going to do now is we're going to create a really nuanced instrument with some code that Max put together, trying to use the same resources that we've been exploring. So now we're gonna create a feedback machine. Is that the plan?
Should I take over?
Yeah. Do you want to use my laptop? Are you okay with that? Yeah.
Yes, I need the mic.
Oh, yeah. Sure. I'll set this one up for you. Sorry, people that are online.
How's that?
This one.
Okay. And people can hear me. Okay, so where are we?
where are the slides? No?
Oh, you can slide to yours.
Ah, here. So, as another application, we thought we do feedback, right? We have a little piezo under the Bela. Maybe you spotted that already. And it's kind of directly on top of the driver, and you'll be like, oh, feedback, right? So we can feed the driver signal back through the piezo into our Bela code. And I prepared a little bit of an environment to do physical models. It's a mass interaction model there. So you can connect these little masses through springs and dampers and build, for example, a plate or a string. So there are some macros to do this, but you could also go and create your own little network of springs and dampers and resonate them within the feedback loop. That was the idea. Most of the time it just screeches and does very unmusical, scary sounds, but that's the idea here. Not sure how musical valuable this will be, but let's just try it out. So you guessed it, it's that piece of code here. And I'm not sure if you can see that.
Yeah, he's probably better on the slides.
Yeah, that's. Ah, yeah, I can hear some feedback there already. Nice. Okay. So you can see in the code, we're using this coupled oscillators library here, and these need a configuration. Right? We can put a configuration. For example, we can put a macro to generate a string with the oscillators, or we can put a macro to generate a plate. And then within the code, we can do a few things, right? We can put our audio input into the model, and then take the output of that and put it onto the driver, right? You can see this further down. And this really sounds nice. Wow, that's it's from them. It's from the. No, that's meant to be sounding like this. That's on purpose. Okay. Maybe let's stop for a while. I just want to add some more words to this, and then you can experiment until the ears bleed. So just to explain the code and what possibilities you have to experiment, I want to say this is, when you scroll down on line, what's that, 103, this is where you actually feed the model with the audio stream, line 103. There you have the audio input from the piezo, that's in, right? And then that generates the audio output here, the variable out, right? So that's where the model feeds through. And here you have a mapping, and that might be interesting. This is the mapping of the touch position of the slider that maps to a string model right now. So what we are actually doing is we are changing the output position of the model with the slider. So we are listening different points of the string, of the virtual string, depending on where we put the finger on the slider. So and if you listen closely, you hear different overtones of the string at different positions. because it will feedback at this overtones, right? So if we made the string longer, for example, you could put a different size here in the constructor, in the configuration. So if you remember, I think 64 notes could also work, so you would have a deeper resonance maybe. I didn't try this yet, so it might be worth trying. And also, if you increase the stiffness, the sound will be higher, right? Also, the more notes you put on, the more realistically will it sound like a string, because it's a very rough approximation of a string if you just put 32 masses on in a physical model. So the more notes you have, the more it will sound like a string. Less stiffness will sound lower. And if you change the model to a plate, you have a richer sound as well. Like you can, if you have a bigger model, I think 8x8 is the biggest size that we can calculate on the Bela right now. So 64 notes, that will almost sound like a gong type of thing. So if you want to try that, just use the plate configuration for here in the constructor, just exchange string conf against plate conf, and then you should have different resonance behavior, and maybe you could also hear the actual plate resonating. It might be interesting to try.
We have to stop and rebuild, or is it
No, you can rebuild
if it's run and you just change the code and you save it, it's better like.
and you save it. It will. I mean, in this case, it will recompile. There's no saving option. It's automatically saving it as well. But if you compile it, it will rebuild the whole thing. Yes.
Okay. Some strange component.
I think maybe this is the one that is sent Clemens. So let's see.
Oh, it's okay.
No, I have another board.
I can do noise too, so maybe this one. Okay, maybe the central. Just go.
So mine is still building.
Still building?
I'm building the plate model, so let's see if that. Okay.
Not working for you? It's not working for the computer. Okay, let me see. I'll bring one of these just in case.
So, and if you wanted to, you could actually initialize an empty model and then do that manually by adding springs, right? And the way you do this is you call this function here, add spring, and then you first you have to tell the size of the model that's empty, right? The amount of nodes that you have. So here in this case 3 nodes, and then you add springs between the nodes. In this case you can add up to 3 springs between 3 nodes, right? 1, 2, 3 springs. And you have to connect them between, you have to give it the left and the right node number. So this would be 0 and 1 maybe. And then the stiffness of that spring. So you could build up your own little models. And also take note that the amount of overtones a model generates is dependent on how many masses you have. So if you have 3 masses only, it's only 3 kind of like 3 sine wave oscillators. So the more nodes you have, the more overtones it would generate. But yeah, that's and of course you have to add a wall, because if there's no node that is referenced to kind of a 0, to kind of a no wall that keeps them oscillating, right? You need to have a pushback force at some point in the system. So this you will do with this code, add wall, and then you just tell it on which node you want to have the wall. And you also need to have so this connects a wall through another spring to the node. But yeah, that's it basically. If you're having fun with this, you can continue a little bit. And I guess then we are ready for the party, Are we?
I hope it was clear. We tried to showcase the idea, give you something interesting and simple. You can play with it for as long as you want, as long as we are able to stay here and change things, and let me know if you have any problem with it. But you can also you can also ask as many questions as you might as many questions as you might want, or if you're a Bela user or you have used Bela before, now's the time to actually put in some requests. If you want. There's a few. I put there a few examples about instruments that have been built taking feedback and haptics into account. There are our blog posts. The slides. These are actually not pushed into GitHub. They're the ones from this morning, and the examples are on GitHub, so those are easily accessible. I'll leave the GitHub link there so that you guys can have it, and I'll send it to Roman so that he can forward it for whoever wants to see it. And yeah, this is pretty much it for today. Good. Thank you.